Okay, in this video, I wanted to go over the central limit theorem for sample proportions. So here's the theorem. Let P denote a population proportion. Proportion is just another word for percentage. And if N times P, so your sample size times P, if that's greater than or equal to 10, and if N times 1 minus P is greater than or equal to 10, then it turns out that the sampling distribution of the sample proportions becomes approximately normal with the following parameters. Okay, so before we get into the parameters, what does this mean? That means that if we take a bunch of samples of size N and recorded the sample proportions for each of those samples we collected, then if we take a bunch of those samples, we're going to have an approximately normal distribution where the mean of that normal distribution, which we will denote as mu with the p hat, the mean of the sampling distribution is equal to our population proportion P, and the standard deviation of the sampling distribution, which we refer to as the standard error. So that is what we call the standard error. And the standard error will be that formula there. The square root of P times 1 minus P over N. And we're taking, like I said, the square root of that entire fraction there. So what does all this mean? This means that if your sample size is big enough, then you can treat your sampling distribution as a normal distribution, which means we can do all of the things that we've discussed before as far as finding probabilities and the like. I want to go through one example here. In a recent city commissioner election, it turns out that 75,147 out of a potential 135,450 registered voters actually voted. What is the probability that in a random sample of 45 registered voters that less than 25 actually voted? Round your answers to 2 decimal places. And I give you guys a hint here. So whenever you're asked in the homework to round to 2 decimal places, to get the rounding correct, what you should probably do is use one more decimal place than what you need. And then at the very end, that's when you're going to round it down to 2. So in this case, because I want 2 decimal places, I'm going to use 3 decimal places everywhere. And then at the very end, I'll round my final answer to 2 decimal places. All right, so here we go. So they want us to find the probability that less than 25 people actually voted in this city commissioner election. All right, so how do we figure that out? So first of all, what are we trying to find? We're trying to find the probability that P hat is less than some percentage. So, all right, so what's the difference between P and P hat? P is your population proportion. P hat is your sample proportion. So what is our sample proportion? So what do we fill in into our parentheses there? Well, let's go through and identify it. P hat will be the number of people that voted divided by our sample size. In this case, our P hat is going to be, we're trying to see if less than 25 people actually voted. So our P hat is going to be 25 divided by the total number of registered voters that we're looking at, which is the 45 in our sample. N is your sample size. Okay. So now, give me a second here. Let's go to our calculator and let's get this this proportion here written as a decimal. So let me see. We can load up. Okay, there's our calculator. So if we take 25 divided by 45, we get the percentage 0.555, a bunch of fives. Okay, let's round out to 3 decimal places. You get a 0.556. So this is approximately 0.556. Okay, So that is our sample proportion. However, this is not to be confused with our population proportion. The population proportion will come up, and we're going to have to use this information that we're given at the beginning of the question. The population proportion is that we know that there's 75,147 people that voted out of a grand total of 135,450 registered voters. This is your population proportion. And what does this equal? Once again, we'll go to the calculator. So I'm going to take 75147. And we divide that by, what was the number? It was 135,450. And there we get a similar percentage here, but it won't always be the case. But here we get a 0.555 as being our population proportion. Okay, with all this being said, what we're saying here is that the question is find the probability, go back up to the top, find the probability that p hat is less than, and our sample proportion is a 0.556. So this is what we need to figure out. And so we're going to eventually use normal CDF in our calculator. And as you guys know from class, in normal CDF, we need 4 things, right? So we're going to use normal CDF in our calculator to calculate this probability. And what do we need? We need a lower bound. And so we're trying to calculate the probability that p hat is less than a 0.556. So that means that our lower bound is a negative 1e99. That's our representation of negative infinity. Our upper bound will be the, let's see, the 0.556. Mean. Okay, so what is the mean of this distribution? Well, this is where the central limit theorem kicks in. All right, the central limit theorem, remember, tells us that, I'm gonna come over here, that the mean of the sampling distribution is the same thing as the population proportion. And they told us that the population proportion is, well, we calculated it, it was the 0.555. Okay. So the mean that we're going to use in our normal CDF is 0.555. Okay, and then lastly, we need the standard deviation. Once again, the central limit theorem helps us out with this. From before, we know that the formula for the standard error, basically, is the square root of p times 1 minus p over our sample size n. So what is this going to look like? Let's see if we can slide over just a tad. This will be, let's see, our p was 0.555, so it's going to be 0.555 times 1 minus that, divided by n, your sample size. Do not get n confused with your population size. So here our n is 45. That's our sample size. We'll divide it by 45, and we will take the square root. Okay. And let's calculate that as a decimal. So let's go back to our calculator. Okay, let me clear this out. So I'm going to do square root. I'm going to take 0.555 and then do open parentheses. So this is understood multiplication. 1 minus 0.555. So notice I haven't closed up my square root yet. And then I still need to divide this by the sample size of 45. And now we can close up our square root. We press enter. Into 3 decimal places, we get a standard error of 0.074. Okay. And this standard error is what we're going to use in normal CDF to calculate our probability. So here we go, putting everything into the calculator. Second vars, normal CDF. Okay, our lower bound, let's clear this out here. Our lower bound is a -1 E99. Our upper bound, if you recall, was a 0.556. The mean was the population proportion, which we said was 0.555. And lastly, the standard deviation that we're going to use is the standard error, and that was, let me double check, that was a 0.074. All right. So notice we use 3 decimal places everywhere. So we're going to go to paste. We're going to calculate this probability. And there we go. We get it a probability of 0.505. So this probability equals 0.505, which if you round that to 2 decimal places, you should get an answer of 0.51, so 51%. So the probability that we have less than 25 people out of our random sample of 45 people that are registered voters, that probability that less than 25 actually voted is 51%, I should say. So to recap, when it comes to the central limit theorem for sample proportions, what you need to do is you have to understand what's your p hat. You have to understand how that differs from your p. And then you need to be able to calculate your mean and your standard error. And then once you have those values, it then becomes just a plain old normal CDF question. And one more thing to remember how we had to the beginning, we had to calculate, the question was, what's the probability that less than 25 actually voted? Keep in mind, a proportion goes between 0 and 1. So your p hat cannot be a number greater than 1 or a number less than 0. So that's why we had to convert that 25 over to a proportion. And we did that by taking 25 and dividing it by 45. All right, let's try one more example. Suppose 15% of people living in a certain city are left-handed. What is the probability that in a sample of 65 people, at least 12 of the people are left-handed? Okay, so once again, we're just going to write down everything that we know. So we are trying to find the probability that p hat, okay, at least means greater than or equal to, but greater than is just fine for continuous probabilities. Greater than some proportion. Well, what is that proportion? We have to figure it out. So p hat, the sample proportion, to figure that number out, you're going to take the 12 and divide it by your sample size of 65. Okay. Here it doesn't specify decimal places, but let's assume that we want to do 2 decimal places. So let's do the same trick as last time. Let's use 3 decimal places everywhere until the very end, then we'll round back down to 2. So 12 divided by 65, let's pull up our calculator. Gives us a sample proportion of 0.185. So that is what we're trying to figure out. We're trying to figure out what's the probability that our sample proportion is greater than a 0.185. Okay, well, what are some other things that we need? Well, we certainly need the population proportion P. This time they give us the P directly. We don't have to calculate it. They told us 15% of people living in that city are left-handed, so our population proportion is that 15%, 0.15, which indicates that our mean, if I can come down here, so the mean of our sampling distribution is the same thing as P, the population proportion, so it's 0.15. And the standard error, okay, will be the square root of P, 0.15, times 1 minus that p over n, our sample size, which is 65. Okay, let's get that to 3 decimal places. So square root 0.15 times 1 minus 0.15 divided by 65. Remember, put all this underneath the square root. Enter into 3 decimal places. We get a standard error of 0.044. Okay. As far as how we're going to calculate the probability, we're going to do normal CDF. Our lower bound this time is going to be the 0.185. The upper bound will be, let's see here, positive infinity. So we'll do 1e99. The mean, which comes from the central limit theorem, will be 0.15. And our standard deviation we're going to use is the standard error of 0.044. Okay, let's put this into the calculator. Normal CDF. Lower bound was the 0.185. Upper bound was 1e99. The mean was, what was our mean? Our mean was 0.15. And our standard error was 0.044. Okay, let's paste that. Let's calculate the probability, and we get a 0.213. And to 2 decimal places, that will give us an answer of 21%. Ooh, fancy. All right. So there we go, folks. That's how you're going to use the central limit theorem for proportions to find probabilities. Hope this video helps you guys out. I will see you in the next.